Some flew for decades, others never returned to service. Car engines and planes, the idea that refuses to die. But which conversions actually lasted under real operating conditions? Car engines and planes, 10 conversions, few survived. Before the troubled programs and empty hangars, one man asked a dangerous question. Why pay aircraft engine prices when a junkyard Ford runs fine? The Pietenpol air camper is where automotive aviation began, and nearly a century later the design remains in active production worldwide. In May 1929, Bernard Pietenpol completed his first flight with a Ford Model A, the same 40-horsepower flathead, four-cylinder engine that powered millions of automobiles between 1927 and 1931. During the Great Depression, when aircraft engines cost more than most families earned annually, he designed an airplane that farmers could build from spruce wood, plywood, fabric, and junkyard parts. The Ford Model A produced approximately 40 horsepower at 2,200 revolutions per minute, with a 200 cubic inch displacement. Simple, reliable, and available for pennies at any junkyard during the Depression era. It was the perfect engine for a budget aircraft. This classic design delivers respectable performance through honest engineering, 29 feet of wingspan with approximately 135 square feet of wing area, and empty weight around 610 pounds, keeping the aircraft light enough for modest power. Performance figures vary by build quality and engine choice, but typical numbers tell the story. Cruise speeds range between 60 and 80 miles per hour, with stall speeds between 30 and 35 miles per hour. Fuel consumption runs 3 to 4 gallons per hour, with range approaching 370 miles, and build time ranging from 900 to 2,000 hours depending on builder experience. Why has this design succeeded where more ambitious projects encountered problems? Pietenpol never promised 200 miles per hour. He delivered something beginners could build and maintain with basic hand tools. The annual Broadhead Gathering still attracts dozens of these aircraft, proving the concept works. But what happens when someone promises twice the power at half the price? The Pietenpol worked because it asked for nothing beyond 40 honest horsepower. Jan Eggenfellner built a business on a different promise. On paper, it made sense. A four-seat utility aircraft with Subaru power at a fraction of Lycoming acquisition cost. The Subaru EJ series, a horizontally opposed four-cylinder engine producing 165 to 230 horsepower depending on variant, seemed ideal for aviation use. Originally designed for the Subaru Legacy and Impreza, between 1989 and 2011, the EJ offered modern fuel injection, liquid cooling, and proven reliability in automotive applications. Between 2000 and 2010, Eggenfellner became the primary supplier of Subaru conversions for experimental aviation, and a substantial number of builders invested significant time and money based on those projections. Then the field reports started arriving, and they told a different story. Originally designed for Lycoming engines producing 180 to 210 horsepower, the Glasair Sportsman is a high-wing four-seater. Builders who installed Subaru conversions encountered a different reality. One owner experienced a serious engine problem at approximately 7 hours total time. Per builder forums, piston damage, oil system issues, and an off-airport landing required. Another discovered reduced cylinder operation without any warning from the engine management system. The manufacturer response tells most of the story. Eggenfellner eventually discontinued his entire Subaru product line and transitioned to Honda-based Viking aircraft engines. Previous marketing materials were removed from public access, and the Generation 3 Subaru was announced as improved but accumulated minimal fleet time before discontinuation. Many builders learned this lesson the expensive way. As reflected in marketplace listings, aircraft with documented Subaru history may trade at notable discounts. Several owners removed Subaru installations and retrofitted Lycoming engines at considerable expense. Not the outcome anyone had hoped for. The transition left existing operators with limited factory support, and the Subaru chapter ended when its primary advocate moved to different technology. An engine with a remarkable fleet record was quietly building hours in the Midwest. Was it really as reliable as the numbers suggested? Here is what the fleet data actually shows. Based on accumulated fleet experience across thousands of installations, factory-assembled AeroVee crankshafts have not exhibited a pattern of systemic failures across the 2180, 2.0, and 2.1 displacement variants over 40 years of continuous development per manufacturer documentation. Thousands of engines operating across the global fleet, and the contrast with some problematic conversions in other airframes is notable. The AeroVee traces its lineage to the Volkswagen Type 1 air-cooled engine, the legendary flat four that powered over 21 million Beetles between 1938 and 2003. Aero conversions modify this proven architecture for aviation, producing an 80-horsepower four-cylinder, horizontally opposed engine with 2,180 cubic centimeter displacement at 3,400 revolutions per minute. Designer John Monnet built the Sonex airframe specifically for the AeroVee from the initial concept phase. Two-seat metal monoplane with low-wing configuration and 22 feet wingspan, assembled with aluminum 6061 T6 blind rivets and laser-cut components. Not a retrofit or adaptation, but purpose-engineered from the first drawing to the final assembly. Reported performance for 80 horsepower consistently exceeds initial expectations. Maximum speeds around 130 miles per hour, with some builders claiming higher after aerodynamic refinement. Economical cruise burning under 4 gallons per hour at 3,000 revolutions per minute, with range between 550 and 687 miles depending on configuration. Climb rates between 500 and 900 feet per minute, varying by build quality and density altitude. Why does this design succeed where some Subaru retrofits and other airframes encountered persistent difficulties? 3 factors emerge from careful analysis. First, the airframe matches the engine characteristics from initial design phase. Second, the manufacturer maintains decades of continuous support with detailed assembly documentation. Third, simplicity dominates, air cooling eliminates liquid systems, and simple carburation avoids electronic complexity. The lesson is clear: design the airplane around the engine, not the other way around. The Sonex showed what happens when you design around an engine from day one. The RV7 community learned a different lesson: $40,000. That is the discount some RV aircraft with Subaru or Mazda engines show compared to Lycoming-equipped examples, per marketplace listings. Builder reports indicate most automotive conversions in this airframe have already been removed and replaced, and buyers factor discontinued engine support into purchase decisions. This is where expectations met reality. The Subaru H6, a 3.0 to 3.6-liter horizontally opposed 6-cylinder engine producing 212 to 256 horsepower, powered Subaru Outback and Legacy models from 1992 through 2019. Some builders believed this modern, powerful engine would transform the RV7 into an affordable, high-performance aircraft. It looked promising on paper. The van's RV7 ranks among the most popular kits in experimental aviation worldwide. Two-seat performance aircraft with low-wing configuration and all-aluminum structure designed specifically for Lycoming engines, producing 150 to 200 horsepower. Performance with Lycoming reaches approximately 207 miles per hour at cruise altitude, and over 2,000 RV6 aircraft preceded it. Weight comparisons reveal a significant part of the underlying challenge. Typical Lycoming-equipped models weigh between 1,100 and 1,150 pounds empty. Subaru H6 installations reached 1,290 pounds empty, according to builder documentation. The additional weight comes from liquid cooling systems, radiators, reduction units, and complex electrical systems. Operators reported elevated oil temperatures and persistent vibration. One aircraft experienced engine computer failure within seconds of its first flight, requiring immediate power reduction per builder accounts. Another builder experienced serious internal engine failure during initial testing, forcing an off-airport landing in a pasture. That owner decided immediately to install Lycoming at considerable expense rather than continue. The RV7 airframe was optimized for Lycoming, and forcing alternatives created compromises nobody anticipated. But what if the problem was never the engine, and always the airframe size? The RV7 Subaru experiment cost some builders $40,000 in resale value alone, as reflected in marketplace listings. What if matching engine to airframe was the real answer? The Hummelbird runs on half a Volkswagen engine, a sectioned VW case with 2 cylinders, and the concept has worked reliably for more than 40 years. Designed by Maury Hummel, who worked in the Curtiss-Wright Experimental Department during World War II, and offered as construction plan since 1983. Single-seat, all-metal construction, with 18 feet wingspan and 13 feet 4 inches total length. The philosophy matches minimal airframe to minimal power plant. The half VW engine is exactly what the name suggests. A standard Volkswagen Type 1 case carefully sectioned to create a 2-cylinder configuration. Output ranges between 28 and 45 horsepower at 3,300 to 3,500 revolutions per minute, depending on configuration, with complete engine weight running only 80 to 103 pounds. Direct drive connects a custom 54-inch propeller directly to the crankshaft with no reduction gearing required. Fuel consumption runs under 2 gallons per hour, creating remarkably low operating costs that make this aircraft a joy to fly regularly. Based on builder reports, half Volkswagen engines have accumulated over 1,500 hours while remaining in active service. Performance exceeds initial expectations for the limited power. Maximum speed around 135 miles per hour in level flight, with cruise between 100 and 120 miles per hour, stall near 45 to 50 miles per hour, and takeoff distance approximately 300 feet. Fuel capacity totals only 5 imperial gallons, but endurance reaches 2.5 to 3 hours with conservative technique. Empty weight around 300 pounds keeps the aircraft remarkably light, with gross weight 530 pounds and useful load 250 pounds. Structure stressed for +6 - 6 G, allowing limited aerobatics, and build time between 300 and 500 hours with costs ranging from $6,800 to $12,000 complete. The Hummelbird proved that half an engine delivers full results when the airframe matches, but chasing maximum speed with minimum budget produces different outcomes. This design has a documented accident history that requires honest examination before any builder commits. Cases attributed to stall spin events at low altitude during pattern operations, structural issues linked to construction deviations from original specifications, and incidents involving pilots transitioning from significantly slower aircraft. The KR2 does not accommodate imprecision in construction or operation. Out-of-tolerance construction creates elevated risk, and the engine is rarely the actual problem. Now we reach the middle of our examination. The design that generates the most discussion in builder communities, the KR2, which demonstrates that automotive engines can deliver serious performance when installed correctly. Compact 2-seater from Ken Rand dating to the 1970s, using wood, polyurethane foam, and fiberglass construction with 20 feet 8 inches wingspan, 80 square feet of wing area, empty weight only 480 pounds, and maximum speed reaching 200 miles per hour. The Volkswagen Type 4 engine, originally designed for the VW 411 and 412 sedans between 1968 and 1974, provides 60 to 80 horsepower from its 1,679 to 1,795 cubic centimeter displacement. Alternatively, the Corvair Flat 6 offers 80 to 100 horsepower. This air-cooled engine-powered Chevrolet Corvair automobiles from 1960 to 1969, and its horizontally opposed configuration makes it naturally suited for aircraft use. Performance commands immediate attention. Cruise around 180 miles per hour at 3,200 revolutions per minute, consuming only 3.8 gallons per hour for better than 50 miles per gallon at 120 miles per hour cruise speed. With Corvair power, experienced builders report 145 knots true airspeed at altitude. Range extends between 1,600 and 2,000 miles with 35-gallon fuel capacity, and takeoff requires approximately 350 feet. The KR2S variant addressed pilot concerns by extending the fuselage 1.4 feet, increasing wingspan to 23 feet, and enlarging the cockpit. Build time typically runs 1,000 to 1,500 hours, with plans available at modest cost. Speed demands respect. This aircraft rewards precision and punishes everything else. But modern automotive technology has evolved significantly, and Honda-based conversions represent a new chapter in automotive aviation. The Zenith CH750 Cruzer with Viking Honda engine represents what automotive conversion looks like when executed with current technology. Cross-country variant of the CH750STOL line from Zenith Aircraft, sharing fuselage and firewall with the STOL model, but optimized for cruise efficiency. High-wing all-metal aluminum structure with approximately 27 feet wingspan. This is where the original promise of affordable automotive power finally became reality. The Viking 130 is based on the Honda L15B engine, the 1.5-liter turbocharged four-cylinder that powers Honda Civic and HRV models from 2016 to present. Producing approximately 150 horsepower at 6,000 revolutions per minute, the complete firewall forward package weighs near 200 pounds, including integrated reduction unit, alternator, starter, direct injection, liquid cooling, and engine management. Developed by the same engineer who previously offered Subaru conversions, he learned from experience and built something better. Installation reports from early adopters describe straightforward procedures. One builder documented a 12-minute engine installation with basic family assistance, with motor mount fitting without modification, per builder testimony. Owners with 75 hours report strong climb performance, reaching pattern altitude before midfield on departure, according to flight reports. Cruise between 105 and 118 miles per hour at normal power settings, with maximum approximately 120 miles per hour, stall around 39 miles per hour, and initial climb near 1,200 feet per minute. Takeoff distances run 300 to 400 feet, depending on conditions, with landing distances 400 to 500 feet, range 400 to 600 miles with standard tankage, and fuel consumption 4.5 to 5.5 gallons per hour, at cruise varying by power setting and technique. Operators report notably low oil consumption and remarkably quiet sound levels compared to traditional aircraft engines. Viking Honda delivers what earlier conversions promised, but not every V6 project reached the runway. Zenith builders report 12-minute installations and solid performance. A beautiful success story. But here's a question nobody seems willing to answer. Why did so few V6 bush plane conversions ever actually fly? Forum archives show extensive theoretical discussion spanning many years, detailed planning threads with engineering calculations, and build logs that start with tremendous enthusiasm, then go quiet. Verified flying installations with significant accumulated hours remain remarkably difficult to locate, and projects appear to stall before reaching first flight. Where did they all go? The Bearhawk Patrol is a two-seat high-wing experimental bush plane designed by Bob Barrows for backcountry STOL operation. Normally equipped with Lycoming engines producing 180 to 260 horsepower depending on variant. Some builders explore the Chevrolet 4.3-liter V6, the Vortec 4300 that powered GM trucks and vans from 1985 through 2014, producing approximately 190 to 200 factory horsepower with proven reliability over millions of units. Greater low-end torque and lower acquisition costs seemed attractive. On paper, the concept made complete sense. In practice, it got complicated. Analysis suggests several reasons why completion rates remain lower than theoretical interest. V6 automotive conversion requires substantial adaptation work that compounds quickly. Reduction units add 60 to 80 pounds and $10,000 to $15,000 to project cost, while liquid cooling systems add radiator, pumps, lines, and another 40 to 60 pounds. Total firewall forward weight runs 100 to 150 pounds above Lycoming. This degrades the STOL performance that defines the Bearhawk mission profile. Cost analysis challenges the fundamental economic premise. Used engine, reduction unit, custom mount fabrication, cooling system, electrical adaptation, propeller selection, and engineering development time. Total investment can approach or exceed Lycoming overhaul costs depending on configuration. Limited completions may reflect builders recognizing these realities mid-project. Sometimes the best decision is knowing when to stop. Corsair Engine Technologies converted a 1969 Cessna 172 to experimental category with impressive results. The test program accumulated approximately 500 hours per company test data. Then regulatory challenges intervened. 3 years. That is how long the FAA took to not respond to a straightforward inquiry. Corsair applied for approval pathways to convert older certified aircraft to experimental category. But according to company statements, meaningful agency response never came despite extended follow-up. After 3 years of waiting, Corsair suspended the project entirely. The technical work demonstrated potential, but the regulatory pathway remained unresolved. The Chevrolet LS Series V8, specifically the LS3 variant producing 430 horsepower from 6.2 liters, represents one of the most successful engine families in automotive history. Introduced in 1997 and still in production, the all-aluminum LS has powered everything from Corvettes to Cadillacs to countless hot rods. Corsair detuned the engine to 200 to 250 continuous horsepower for aviation duty, with electronic fuel injection and redundant ignition systems. The converted 172 delivered performance substantially exceeding original factory capability. Takeoff distances reduced by approximately 500 feet compared to standard, with climb rates described as nearly double production models per test program data, cruise speeds reported at 120 to 130 knots true airspeed, with operating cost estimates around $20 per hour, based on automotive fuel prices, though actual costs vary by location and utilization. LS engine architecture offers theoretical advantages for extended service life. Automotive applications routinely exceed 200,000 miles, suggesting potential for 3,000 to 4,000 equivalent flight hours. The test aircraft accumulated over 500 hours, including primary flight training, check rides, and cross-country operations, with performance remaining consistent throughout the program. Then regulatory process halted further development, despite technical success. The FAA spent 3 years not answering, and the Cessna conversion stalled waiting for a response that never came. But experimental aviation offers a different path. No permission required. That is what experimental aviation offers when certified pathways remain closed. The RANS S12 with a Viking Honda engine demonstrates what individual builders can accomplish without certification requirements. Ultralight and experimental two-seater with high wing design, produced by RANS Incorporated since the 1990s with continuous factory support. Known for engine versatility, accepting Rotax 447, 503, 582, various automotive conversions, and Rotax 912 series, with 31 feet wingspan and 152 square feet wing area. The S12 closes our examination for one specific reason. It demonstrates that builders can succeed with automotive engines using currently available components and active manufacturer support. One builder documented completing 2 RANS aircraft with Viking Honda installations without major complications. Installation described as straightforward, requiring approximately 12 minutes for basic engine mounting with family assistance, and motor mount fitting without modification, per builder testimony. Thanks for watching. If you found this useful, subscribe, like, and leave a comment telling us your thoughts or questions. Turn on notifications so you don't miss future deep dive analyses and practical tests. Watch the videos that appear on the screen and continue with us. Bye-bye.